Hello there. I wanted to give you a walkthrough of ChiliPeppr Hardware Fiddle's new auto leveler for PCB milling. So for any of you who are making PCBs on your CNC machine, this is a video for you. So you can see we're at the ChiliPeppr.com homepage, and I'm going to go into the TinyG workspace. And it's got a new auto level feature that has been added. I do a lot of PCB milling, and there's this new button up here, and it might seem like a pretty simple little button, but the power behind it is pretty immense. This auto leveler is specific to the TinyG right now. Let me actually go ahead and I'm going to collapse this Gcode widget and then open up the auto leveler. Notice that it immediately tries to actually let's autofill that again. It immediately tries to run a probe area. I'm not going to do an auto level for a PCB on that ChiliPeppr code, but what I'm going to do is I'm going to load a previous file, or I'll show you what's more of a typical scenario is to load a like a .tap file, a tap file. Now this file, this is an Arduino Shield I've been working on. I'm just going to drag it over to the browser, and it is, you can see it's sort of shaped like an Arduino Shield, and this was generated out of the PCB Gcode utility that is available for Eagle, and it's a pretty common tool set that a lot of makers are using out there to generate the Gcode for PCB isolation. You can see all these little blue lines are where the milling bit would run, and I've got some really detailed work in here. In fact, this part right here is a surface mount device that has really very fine traces. So the finer the traces you have, the more important it is to be able to auto level your PCB, because your PCB may look pretty flat, but there's sometimes like a 0.1 or 0.2 or 0.3 millimeter difference in different parts of the PCB as you're milling it. So I'm going to go ahead and turn auto level on, and notice it automatically surrounds your Gcode. It looks for the extents of your Gcode and then tries to create a nice probing grid for you to probe the regions. I'm actually gonna connect to my TinyG. It's right here on my COM22. Notice the moment it does, it's able to get the values from the TinyG, and I'm gonna turn off the look at toolhead and go back to the extents. And then I'm going to go open up my WebRTC client, because I actually do have a video feed. This is a pretty new feature as well, where it is able to stream video over WebRTC into the browser environment. And this is pretty darn helpful, because usually I will let the machine kind of run while I go elsewhere in the house, and I still kind of want to watch what it's doing. So it's pretty cool. So notice though, I've got this new auto level widget right here. There's some new features to collapse other widgets, because space is starting to become a little bit of a problem inside this environment. I still want to make the 3D view be kind of the centerpiece. So let's get started though, doing the probe. You'll notice that there's a few tabs here. There's a pre-run tab, a run tab, and a post-run. And it's because there's really kind of three steps. There's this initial step, which is setting up where you want the probe stuff to happen. It automatically clicks the autofill button for you, and that's just reading all these extents. But I want to show you, if I wanted to increase the amount of probe areas to get higher resolution, I could just come over here, hit the down arrow a couple times, go to 2 millimeter, and just tab out of it, and notice that there's even more probe regions to do. If I really wanted to get huge accuracy, I could even go down to 1 millimeter. That's probably overkill, because you're not going to see that much difference every 1 meter. So I like kind of leaving the defaults actually at 5 millimeter. If you wanted to, probe a wider area, you could do that, but there's almost no reason. So I feel like the autofill pretty much does what you need. And then these other settings are, the clearance height just means how high it will move the z-axis after a probe, when to actually sort of slow down and really go at a lower feed rate so that the end mill, as it's you'll see that the end mill's got a little alligator clip on it to complete the circuit. You want it to move slow towards the PCB so that it's not doing bigger increment steps. You get a little bit of better accuracy. So you could probably frankly do something like that, 0.25 to start the probing, because that's when it drops down to this feed rate, because it really is going to run a G0 command from this 1.5 to this 0.25, which means it'll run it at the full feed rate that you've set your TinyG to run at. But I'll just leave the defaults for now. Actually, no, I won't. I'll go to 0.35 because I've done a probe before, and I know that at my worst spot I'm at about a 0.3 millimeter. And then the max negative Z, you don't really need this, but it's kind of a safety net in case the circuit doesn't connect. That shouldn't happen, but I found that if there's noise on the wires that you've connected, you can see this yellow line here, but there's also a blue line that is actually soldered to the PCB to make sure that there's a really good electrical connection. And then the most important part is that these wires run to the Z-min switch on the TinyG to complete that circuit. So now that we've got that going, I'm pretty much, I can turn off this region to probe if you don't want it there. But I'm going to go to the run, and there's a play and a pause and a stop, but there's also this run test probe, and there's a whole explanation here on what all that, what to look for and what to watch out for as you run this and how it works. But I'm going to run a test probe. Notice that my tool head is not quite in the 0, position. Not a big deal, but I'm going to run a test probe, and so watch what starts happening. It starts lowering the z-axis, and you can kind of see it lowering. It's hard to see it in the video because it's lowering at a pretty slow feed rate, but I'm getting down here, and as I get towards 0, it will complete the circuit on the Z-min switch, and it should stop moving the Z immediately. So we'll probably get pretty close to 0 because I had this previously calibrated. Okay, so we're at 0.017. So that shows, though, that the test probe ran fine and that you're pretty much ready to go with your job. So let's just go ahead and kind of raise that back up a little bit. And we are ready to hit play. Again, we're going to probe 180 locations here, starting with location 1. So you can either hit play here or hit play up there. Really, a lot of these buttons up here are being regurgitated down here. But in case, after a while of using this, you might actually just only use these toolbar items. So I'm going to go onto the Run tab and hit play. There's a warning message that pops up just to say we're about to start auto leveling. Make sure you've got all your wires connected correctly. I already kind of went through that. The only dangerous part is that if that circuit does not connect, like if you have a little piece of dirt on your circuit board, on your blank PCB, or like a piece of tape that you're probing, which I've done, you're not going to complete the circuit and you're going to have a mess. You may end up breaking your end mill, depending on how thick it is, or other damage to your CNC machine. Frankly, I've had it happen where it just is making the z-axis be skipping on the motor. So let's go ahead and get probing. So notice it's going to 0, 0, x 0, y 0, and then it's descending towards. There we go. We hit our first point. So this point that we just hit, I'm going to zoom in there. That point is set as the true 0 because it's the first one on the board. And then every point after it is set as an offset. So you can see this one is only 0.009 in the negative, and this is 0.015. Those are pretty tiny offsets. It doesn't matter that much, but the 3D view is showing you a little bit of a matrix to help you visualize some of the warpage. So you can see it'll just keep re-rendering as it goes along, which I think is a pretty cool feature. But I will point out that these numbers don't really correspond to how exaggerated the warpage is showing. And the reason for that is this right here. The default is a 50x matrix exaggeration. I'll drop it to a 10x. You can see it's pretty subtle there. But if you go to a 1x, it's almost you almost can't even see it. So that's the reason I added that feature, was that I wanted to really visualize the delta. In fact, it's kind of fun to make it 100x and just sort of see how extreme it gets. Yeah, so we'll let that run. So take a bit. While it's running, I'll describe some other aspects of this for you. Let me switch this back to 50 because I think that's a more reasonable. Okay. So you are seeing this run in the WebRTC client. You do have to run the WebRTC server workspace for that to work, and I will show you really quick. That's just chilipepper.com/WebRTC server. I won't hook it up to any video, but in fact it's saying that I'm already sort of connected, but I'd have to allow it. So we'll leave that alone, but that's the two components to this video feed. Since something like a probe takes a while, this is almost like the perfect chance to have this little video feed and kind of move on and go grab a cup of coffee. But back to the probing itself. Excuse me. As we're running here, I'll show you some of the stuff you can do. So this area right here really has to do with the matrix, and the matrix is this brownish looking, it's the data that's being produced from the probe steps. And this first icon, I'll show you this post-run tab because these icons correspond to each other. So this icon right here is view probe data. And then this is show the matrix. You can just toggle it off, and then you're just seeing it move and you're not exactly sure what it's doing. That just toggles it back on. Let's go ahead and view the probe data though, because I want to show you what it looks like. So it's just JSON format. And this is the first chunk of data, x0, y0, z0, and then you'll notice here, remember this was the -0009, which we saw in this first probe step there. And just to set true done true, when it starts the process it sets sent to true, and when it's done with the process it says done to true. So it's just a flag to keep track. To some degree it doesn't have to be kept track of in this JSON content. But the reason why this is worthwhile is that if you want to just start cutting and pasting or saving it somewhere to like a file, because you can load your data later by pasting that JSON in here. Or you can well, and then you can bring up previous files. So the only way to load previous probe data right now is by pasting it right here. The project will get stored in your recent files list when it's done automatically, but it only does do that after you've completed the probe. So that's a little bit about how the files work. You can also then view your final Gcode and send your Gcode to the workspace right here. Now I could go ahead and run it, but it's a little bit pointless because we don't have all of our probe data. So I'm not going to get any modified Gcode just yet. Well, maybe I will for the sake of... No, what I'll do is I will pause this video and come back when the probe is done running so that I can show you exactly what the G-code will look like once everything's completed. Okay, I'm about halfway through the run, and you can see that there is a lot of warpage in the middle of the board. So it started out going negative, where it was below this first probe point, and these points near the middle of the board are raised. So we will see how we finish up on the board, but that's pretty significant warpage, although even then, because it's exaggerated, I think the worst spot here is just 0.1 millimeter, so it's not too bad, kind of expected. Okay, we are probably 3/4 done here, and just to give you a little preview, our worst case is probably the probe we just ran, which is at 0.223. So 0.2 of a millimeter. I'm going to switch this back to 1x just to kind of show you that although it looks bad, it's not really that bad. But if I'm trying to mill a 0.1 millimeter depth or even less, I've got some really thin, some small end mills to get some narrow traces, and in that case I typically want to just go to 0.05 depth to be able to go really slow and not break the end mill. So this is pretty important to see. In fact, this information, what I'm finding is I probed this board a couple days ago, and I had different data. It was actually generally the same direction I'm seeing, but I actually feel like humidity can affect the board shape. So if you're going to run this probe data, you probably want to run your actual milling job shortly thereafter so that you're not getting old data due to things like humidity, so or even heat, because I've got a window right there projecting onto the CNC machine. So we're almost done. I'll come right back at the end. Alright, we are just about on our last step. I'll take you. Okay, we're done. So the you can see in the status here, created a recent probe data entry for you called probed 180 locus. That is available right here, and it puts the timestamp next to it. It's about 17 kilobytes of JSON data, and that is now stored in your browser's local storage file. So you've got it in the future, at least in this browser. And now the final step is to modify the G-code. So this is done for you automatically, and we'll go ahead and view the auto-leveled G-code, and I'll show you what we get. So this was generated by the PCB G-code, so there's a bunch of comments at the top, but if we go to the first G0 value, it modified the 2 back to a 2. So really there was no modification at all. And that makes sense because this is the x0, y0 position, which we made be our absolute 0. So there shouldn't be. In fact, if you want to kind of double check everything went correctly, even this new z that was added. When there's a modification of an existing z, you'll see the mod. If it's a new z being added, the goal is to add a z to every single line possible so that you get the best resolution in your G-code for matching the warpage. As we get down here, you'll see there's a new z added. It's 4 decimals in, so it's barely a change, but you're already at least seeing a little tweak. This was a 1, a negative 1, and now it's a negative 0.0995. To get these coordinates to go in here with these modified values was maybe one of the tougher parts of the code, because you've got to raycast this brown matrix onto the XY values and Z values of the original G-code. But it's working great, and you can see there's just a lot of new Z's being added. If I went way to the bottom, you'd see all of them. In fact, I'll just scroll to the bottom really quick. And you know, the last one, where are we at? We're at 5312, so we're at X53, roughly around here, is a pretty big shift. So this was a modification. It was negative 1.75 and it's now negative 1.544. So about a 0.2 millimeter modification, which I think is pretty normal for the warpage you see on a PCB. So we'll close this. I will send the AutoLevel G-code to the workspace. This is the equivalent. I'm going to turn off the matrix now. This is the equivalent of coming up here and dragging and dropping or pasting in the G-code right here. Notice though now we have a new file that I just created. In the recent files, it's just called AutoLeveled with the first sort of few comments from the G-code. I can now turn off the AutoLeveler, open back up my G-code widget, and my new G-code is loaded. Let's make sure that it has, yep, it's got my new comments in there, and I'm ready to now run the job. So hopefully you have lots of success with auto-leveling your PCBs before you mill, so you get perfect mills.